Okay, so welcome to Math 150 Multivariable Calculus. This is the second lecture. And what I want to do today is talk about some background material that you should have seen before, but given that it's been a while since some of you have done calculus, it's not a bad idea to review some of it. Also, by doing so, we can talk about how do you think like a mathematician? How do you tackle a new problem and come up with a conjecture as well as a way to try to prove it? And so the goal today is to really talk about mathematical reasoning. How do we know how to do the steps we do to get to the answer? And as you go further and further in your careers, if you are on the scientific quantitative side, you're going to have more involved, elaborate formulas. One of my thesis students had an equation that spanned, when he was doing his defense, 40 pages. And so how do you make sense of something that large? How do you try to find tests to see, is this reasonable? And so what I want to do is I want to do this by starting with something that you've hopefully seen before, the Pythagorean theorem. So there's often more than one way to prove something. So we say a proof in a math class, not the proof. And different proofs will highlight different aspects of the problem. And sometimes one will be better for generalizing than others. And it's not always clear which is the best one. And that's why there's a value for, even if something is known, it could be worthwhile to find a new way to do it. A lot of times you get involved in just doing a lot of tedious algebra. And so the goal is to try to figure out a way to understand the mess that's coming. And so frequently what we can do is we can look at a special case and use our knowledge of the special case to try to get a sense of what's going on and to gain some real insight. And so as I said, the motivation for today is the Pythagorean theorem. So what is the Pythagorean theorem? Well, really the only flexibility I have is which side do I want to call A and B, and where do I want to draw, which way is the triangle oriented. So I've got a right triangle with sides A, B, hypotenuse C, A squared plus B squared equals C squared. Okay, so there's a lot of proofs. So this proof goes back over 2,000 years. It goes all the way back to Euclid, probably goes back earlier than that. And the first thing you notice is you start off with the triangle, and then you draw 3 squares, and you draw a lot of extra lines. Most good geometry proofs at some point have you drawing extra shapes, often extra lines. How do you figure out which lines to do? Well, with anything, like anything else, the more times you do it, the more experience you have. The more experience you have, the more likely you are to know which way to draw things. We're trying to prove something about right triangles. So this tells us maybe we want to draw lines in such a way that we get right triangles. Well, if I draw the line from B all the way down to the side EN, that's going to give me a right angle. And then if I draw the line BE, that's going to give me a right triangle. And so if you start thinking about this, this might give you some idea of what's going on and why these choices were made. But I still find this proof a bit hard to follow. I find it hard to follow even if you put things in color, although the color does help. Say, oh, okay. So I'm probably going to try to somehow show that square, CJLE is the same area as the square CAHI. And similarly for the two goldish areas. This proof scares me. Yeah. What do you think must be true about the coloring scheme? And again, when you make comments, remember to email me after class about the comments you make. So what would you guess must be true based on how things are colored?
That the areas are equal.
That's okay, everybody speak at once.
The same color areas are equal in area.
Yeah, the same, right. Now, how the hell someone came up with the idea to color things in this way and to divide things? Well, let me see, I can look at triangle 1 in the original and see, well, maybe I'm using the hypotenuse to be the side of the thing going down on the bottom. And then maybe one of the side lengths, or maybe not the hypotenuse, maybe it's one of the sides, and that's giving me like the flipped triangle down there. And so as extra credit, if you actually want to go through and try to prove that this works, that you can split everything up without overlap and this works, that's great. The fact that you have this in front of you is a great hint. It is terrifying me to try to think of how I would come up with this on my own. This is the first proof I can recall seeing. I saw it as a freshman at Yale in a physics class that I remember, and it's a really nice proof of Pythagoras. And so what we do is we have the big square of side A plus B, And then we have four triangles, four right triangles AB. And we're assuming two facts. We're assuming that everybody knows that the area of a rectangle is base times height. And thus, if I take a right triangle, that's just half of the rectangle. And because the two halves are similar, I can rotate and translate one triangle into the other, and that shouldn't change the area. The area of a right triangle should just be 1/2 base times height. So the four triangles give me 4 times 1/2 AB, or 2AB. With a little bit of work, you can show that the rhombus is actually a square inside. So all the angles between the C's are 90 degrees. So its area is C squared. So A squared plus 2AB plus B squared has to be C squared plus 2AB. Cancel the 2ABs, and we get A squared plus B squared is C squared. So we've proven Pythagoras. Another proof is to do a little bit of shuffling. So we take our triangles, as we did a moment ago, and if we move them around a little bit and form rectangles that meet, then I'm going to have one square of side A and one square of side B. So A squared plus B squared has to be C squared. So it's another nice, beautiful geometric proof. This is Williams College. What is James Garfield famous for? Well, a lot of people would say being president of the United States of America. But as a mathematician, I will point out to the fact that he is credited with the proof of the Pythagorean theorem. So his proof uses a trapezoid. As a Williams professor, I will not comment about if that is really very similar to this proof, but he is credited with a proof of the Pythagorean theorem. Does anybody know what Garfield was doing when he was assassinated?
Wasn't he on his way to a class reunion?
Yeah, I believe he was on his way to his 25th class reunion. So extra credit for you, well done. So there's lots of different proofs of Pythagoras. Just because I've proven something doesn't mean I understand why it's true. I've just done the algebra, I've just done the geometry. How do you find these combinations? Is there a reason why this is working? Is this surprising? Do you know why it's true? And so what I want to try to do is talk a little bit about dimensional analysis. This is a phenomenal way to get a sense of what the answer might be. So if you take I think I first learned this in chemistry class, in terms of just being really careful in putting the units in everything and never drop units. And you might say, well, this is a math class, where are the units? You can put units and integrals and all the stuff that you're doing. And when you're doing this, if you put in these units, it can help you figure out what the answer might be. So I'm going to propose 5 possible Pythagorean theorems. They are all wrong. 4 of them are wrong in obvious ways that we can immediately eliminate. And one of them is wrong in a subtle way that we really can't eliminate until we do some work. Does anybody want to try to argue why one of the 5 is wrong? And if so, how? Why it can't be right?
I guess the second one is obviously wrong because if you look at c squared equals a squared plus 17b squared,
Yes.
I guess that what you could do is that you could go and set up the area, or I guess, so you could use, I guess, the unit circle to go and prove that wrong and prove that, I guess, there's no relationship, I guess, in general between b and 17. So I guess the 17 coefficient.
So 17 is suspicious.
Yeah.
I grant you that 17 is suspicious, but it would be a lot of work to show that it can't be 17. You're on the right track. There is something about the presence of 17, or you might even say the absence of 17 somewhere in this equation.
Well, it would be correct if you added the 17 coefficient to the a squared and c squared terms.
Right, I wouldn't say correct. It would be in the running.
Okay.
The fact that it's asymmetric makes me suspicious. There really shouldn't be a difference in the role between A and B. And yet this is making A and B come in asymmetrically. So I'm a little bit skeptical about the second equation. Anybody want to give me an issue with the third equation?
Can I do this one?
Sure.
Sick. So a squared minus b squared is going to give you something that's smaller than a squared.
Perfect.
And then we know for a matter of fact that c is bigger than a, so it just can't work.
Just can't work. Absolutely. And in fact, if b is larger than a, it gives you c squared as a negative number. What about the first equation? C squared equals a to the 17th plus b to the 17th.
I feel like logically it just seems illogical, like to the 17th power is like such a huge number that c would have to be like, it just doesn't make sense.
It seems suspicious,
Um,
but there is an explanation you can give as to why it can't be right.
I can do this one, I think, potentially.
Okay.
C is cannot be greater than a plus b.
Good.
And
So
so if you had like, if a is 2 and b is 2, c could not be greater than 4, and that wouldn't work.
good. So you know C is at most a plus b. If you take the remarkable situation where a and b, you have an angle of 180 between them. That's the largest C you can get. So if you do that, that would eliminate 17. It wouldn't eliminate maybe a to the 1.5 plus b to the 1.5. So another way to eliminate 17 is to think of units. If C is in meters, C squared is in meters squared, but a to the 17th is in meters to the 17th. So the units don't work. Now, what's nice about the argument you just gave is that immediately eliminates the fifth equation. The most C squared could be is a squared plus 2ab plus b squared. 17 is too large there. But a squared plus ab plus b squared is legitimate. That has a chance. So this is just summarizing what we've just said as to why 4 to the 5 can't possibly be right. But before you try to prove something, it's nice to have an idea of what it might be. Now, there's also a danger, of course, that if you know what you're trying to prove, that could influence how you view your data. So what I want to do now is I want to give a dimensional analysis proof of the Pythagorean theorem, and then we'll apply dimensional analysis in another setting just to show you how powerful the technique is. So let's assume we have a triangle ABC, we have an angle X, and I claim that the area is a function of the hypotenuse C and the angle X. And if you remember your trig, B is just going to be C times the cosine of X, A is going to be C times the sine of X. So the area is 1/2 AB, it's 1/2 C squared sine X cosine X. If you look at it like that, even if we don't know what sine and cosine are, we immediately see that the area is proportional to the square of the hypotenuse. If I triple C, I triple A, I triple B, so the area goes up by a factor of 9. So I can write my area, which is a function of C and X, so we're doing multivariable calculus, we have a function of two variables. I can write it as f of X times C squared, where f is some unknown function. And we see that the area is proportional to the hypotenuse squared. Now, as I remarked, all good geometry proofs at some point require you to draw a line. So we need to draw a line, but where? So does anybody have a thought about how I can draw a line and get some right angles? So any thoughts about where I could draw a line and get some more right angles?
Is it possible?
I don't know if this would actually work, but maybe if you drew like a line from the hypotenuse C to the intersection of A and B, and made sure that it was, yeah.
Yes.
Cool.
So that works, and it's called the altitude. And I generate two new right triangles from this. And in a flash of insight, I named them triangle 1 and triangle 2. Boring names, but they combine without overlap to form the original triangle. And if you do a little bit of geometry, you can see that the new triangle 1 also has an angle of X, which means the three triangles are all similar. And we know that the area is proportional to the hypotenuse squared, and the proportionality constant is a function of the angle. Well, they all have the same angle. So I know f of X times A squared is the area of the first triangle, f of X B squared is the area of the second triangle, and that sum must be f of X C squared. the area of the whole triangle. What can I do now?
Divide by f of x.
Okay, now this is a math class. This is not an economics class or a physics class. So what must I do before I divide by f of x? What do I have to check? If you don't think there's anything to check, you can be a physicist or you can be an economist, but you can't be a mathematician. What do you have to check before you divide by f of x?
Would it be that f of x is the same for all three?
Well, no, we know it's the same for all three. You know, they all have the angle x. So it's, otherwise I couldn't write f of x. I maybe have to write f of x and f of y. But before I divide by a number, what do I have to check?
You have to check that f of x equals not 0.
I have to check that f of x is not 0. Well, what would it mean for f of x to be 0? It would mean that the area is 0, which is absurd. So I know f of x is not 0, so I can divide by it. But you've got to be very careful. Whenever you divide, you have to make sure the denominator is not 0. And now we have Pythagoras. Now here's another example with dimensional analysis. So imagine you have a pendulum. It's hung from the ceiling and it's swinging. You have the force of gravity pulling it downward. The length is measured in meters. The acceleration due to gravity g is in meters per second squared. The mass is in kilograms. The period is how long it takes to get from where it started back to where it started. And the initial angle that we release it at is x, which is radians, and radians is unitless. So radians has no units, and we'll talk more about that later in the semester. So if the period is in seconds, I need to combine the length, the acceleration, the mass, and the angle in such a way that I get units of seconds. Can anybody see how to combine them to get units of seconds? Or can anybody tell me something that doesn't come into play in combining them?
The mass wouldn't affect it.
Yeah, the mass can't affect it. Because the mass is in kilograms, I have nothing that cancels kilograms. So before we even do the experiment, we know that the period is independent of the mass. We're assuming, of course, that there's no force other than the force of gravity. Okay, so now we just have length, acceleration, and angle. Well, the angle is unitless, so there's no way to tell how that comes into play. So we're left with just length and acceleration. How can you combine length and acceleration and get seconds?
But if you divide length by acceleration, you're left with seconds squared.
Good. And so how can I go from seconds squared to seconds?
Take the square root of it.
Take the square root. And so I get that the period has to be some function of the initial angle times the square root of L over G. So before we even go to the lab, I conjecture that if we quadruple the length, the period doubles. It turns out to first order, the period is independent of the angle x. But again, this is the power of dimensional analysis. We now know the functional form without even developing any advanced theory. It's just the only way we can combine the quantities. So what I want to talk about now is how might you guess the Pythagorean formula? And again, we all know the Pythagorean formula. We've just proven it, in fact, less than 10 minutes ago. But the point of today's lecture is to talk to you about how do you view mathematics? How do you view a new situation? How do you gather data and make a conjecture? Well, let's try to guess a functional form for the Pythagoras. We're going to have some free parameters, and we're going to look at some special cases and try to figure out, can we find values that work in the special cases that we can compute? And again, there aren't that many special cases that we can compute. Now, natural guesses is, let's take the simplest formula we can think of. We guess that the formula should be symmetric. And maybe the first one is that it's linear, that C is just some linear combination of A and B. If that doesn't work, we could try a quadratic. So maybe c squared is something involving a squared, ab, and b squared, and so on and so on. But of course, that's not the most general quadratic. You could have terms like AC, BC as well. All right, so let's guess the special relationship C equals alpha A plus beta B. So again, this is clearly going to be wrong, but let's see if we could make it work. Let's try to consider some special cases. Can anybody tell me anything about these unknown alpha and beta?
They have to be less than 1.
They have to be less than 1. Why do they have to be less than 1?
Because A plus B has to always be less than C for it to be a triangle.
No, C has to be less than A plus B.
Is it because of, I guess, in a unit circle, that C would have to be equal to 1?
I mean, you can always, of course, assume that C equals 1, but then that gives you new values of A and B. So what can you tell me about alpha and beta? If you know alpha, do you know beta? So what do you think the relationship is between alpha and beta?
Do they equal 1 when they're added?
Well, okay, so that's one possibility, but just even more basic. If I tell you alpha, do you know beta? Think back to the example we had with, a squared plus 17b squared. We didn't like that because it was asymmetric.
They have to be the same.
Yeah, alpha and beta should be the same. We shouldn't be able to tell the difference between A and B. And so if we take A equals B, we know C has to be less than A plus B, right? Less than or equal to A plus B. So we know alpha plus beta has to be at least 1. So we can start trying to think a little bit more about how large can alpha and beta be. So we want to consider some very special triangles. The problem is we don't know the Pythagorean theorem. So we want a triangle where we can approximately determine A, B, and C. Does anybody have any thoughts? This is the hardest part of the argument of what might be a good triangle to look at. So what kind of triangle? You might say, well, we like right triangles, 45, 45, 90, but we don't know the Pythagorean theorem, so we don't know it's 1, 1, root 2. You might say we like the 30, 60, 90 triangle because that's splitting an equilateral, but we don't know Pythagoras. So what kind of triangle would you want? This is the hard part.
Would we want an isosceles, like 3 sides, same length?
Well, if we have 3 sides of the same length, it's not a right triangle. And we don't know the Pythagorean theorem. So if you look at a limiting case, what could you send A or B to and keeping the other one fixed?
One of them could go to 0 and the other could go to C.
Yeah, so if one of them goes to 0, so if you consider a very thin triangle with A going to 0, then B is going to go to C. Or if you have B going to 0, you get another thin triangle and you have A going to C. And so if we send A to 0, B and C converge to the same thing. And so you have to have beta equals 1. And if we do it the other way, we get alpha equals 1. Or we could have just said we believe alpha and beta should be the same, but this is a little bit nicer. So by looking at special triangles like this, we know as we go thinner and thinner and thinner, B and C or A and C are almost the same. So the only possibility is if beta and alpha equal 1. And so does C equal A plus B make sense? That's the only possible linear relationship. Well, as remarked, we have two facts that we're using. We're using the area of a rectangle x by y is xy, and the area of a right triangle of sides x by y is 1/2 xy. So let's take a special triangle where we take two sides to be 1. And we're going to take the isosceles right triangle, and we're assuming C equals A plus B. So if C equals A plus B, the hypotenuse has to be 2. So we now have a square that's 2 by 2, and the diagonals of the square equal 2. Well, we can calculate the area in two different ways. One is it's a square, so the area is just going to be 2 times 2, which is 4. The other way is we have 4 right triangles, and each triangle has area 1/2 base times height, so each has area 1/2. We have 4 of them, so that gives us 2. So since 2 doesn't equal 4, we know that there can't be a linear relationship for Pythagoras. So if we have a right triangle, it has to be more complicated than C equals A plus B. And what I love about this is we've proven a little bit about what the answer can't be. We don't yet know what it is, but we at least know what it is not. And that is making progress. So now let's consider a quadratic guess. C squared is alpha A squared plus gamma AB plus beta B squared. Can anybody tell me anything about any of the alpha, beta, and gammas?
For similar logic to the previous one, alpha and beta probably have to be 1.
Yeah, they have
Because
to be
if-
1.
Yeah.
Yep. So what we could do is we can look at the same thing of just taking really thin triangles again. And if we take really thin triangles, we'll again get alpha equals beta equals 1. The difficulty is gamma. So now what we can do is we can take, again, isosceles right triangles, 1, 1, and C. And what we can do is we can try to figure out, could this work? What would gamma be?
Wouldn't gamma have to be 0?
So we're going to get that gamma has to be 0. So we equate areas. So one way is, the area is C squared, but it's also 4 times 1/2, which is 2. So C squared equals 2, or C equals the square root of 2. Well, if C squared equals 2, we get 2 equals 1 plus gamma plus 1. So gamma has to be 0. So C squared equals A squared plus B squared. Did we just prove the Pythagorean theorem? Did I just give you a new proof of the Pythagorean theorem? Yes or no? So it's really important to recognize when have we proven something versus when have we provided evidence. And unfortunately, it is very easy for people to misinterpret what you say. I have not said we have proven the Pythagorean formula. All I have said is that if the Pythagorean formula is a quadratic relationship, then it must be of the form C squared equals A squared plus B squared. At least under the assumption that there's no AC and BC terms. I have not proven the Pythagorean formula. I've just said this is the only possible form. So you've got to be very careful. Can somebody tell me in lowest terms what 16 over 64 is?
A 1/4.
1/4. 19 over 95.
1/5.
1/5. 49 over 98. Let's make it a little harder.
1/2. Ooh,
1/2. Let's do one more. 12 over 24.
1/2.
I'm sorry?
1/2.
I get 1/4. Does anybody else get 1/4 or 1/2? So somebody else should get either 1/2 or 1/4. Could somebody else please speak up? We have one vote for 1/2 and one vote for 1/4.
1/2.
Okay, I got 1/2.
1/2.
All right, this is not good that we are differing. Do you want me to show my algebra?
Yes.
Let me show my algebra. So 16 over 64, we cancel the 6's, we get 1/4. 19 over 95, we cancel the 9's, we get 1/5. 49 over 98, we cancel the 9's, and we get 4/8, which is 1/2. So obviously, 12 over 24, we cancel the 2's, and we get 1/4. Okay, this is not a valid proof. Just because something works in a couple of cases does not mean that you've proven it in general. The way you divide two-digit numbers that have the same number on the anti-diagonal is not by canceling them. There's a whole slew of things you can find like this, that these formulas that work in some very special cases. But just because it works in a special case does not mean it works in general. And in fact, here's the proof. 12 over 24 is not always going to, in fact, it's never going to be 1/4. This is not how you do it. What I could have done is I could have actually just shown you the 16 over 64 and the 19 over 95 and kept 49 over 98 in reserve, so that if you doubted 12 over 24, I could say, let me choose another fraction and I'll show you that it works. Let's take, oh, I don't know, for kicks and giggles, let's take 49 over 98. So again, be very, very careful when you're doing things about the difference between proving and providing evidence. All right, so what I want to do is start to move now towards new material and use this as an opportunity to introduce math that we're going to be seeing a lot in the next few weeks in multivariable calculus. And we're going to do this by asking a question that you could have asked as soon as you saw the Pythagorean formula. What would the Pythagorean formula look like on a sphere? I did not even think of asking this until I was a professor at Williams and I was talking to Professor Garrity. And we were both just amazed that we had never thought to ask this earlier. And of course, we proved some results, and then we did some web searching and we saw that, of course, this was well known, as we expected it was. We never thought this was novel, but it's interesting how easy it is to just be moving along a path. You need to stop sometimes and think and explore. How can I generalize this? And a lot of times, this is how you can really make your name. If you can take something that's known and push it further and come up with a new setting. So I have written papers in accounting, computer science, economics, geophysics, physics, marketing, sabermetrics, statistics, operations research, so many different areas. It's the power of being trained as a mathematician. You're trained as a problem solver. What changes is maybe the meaning of the variables. And so what I want to do is I want to talk about what would the Pythagorean formula look like on a sphere? And this is going to be a great way to introduce a lot of the concepts we're going to be studying in the course. So let's imagine we have some triangle with vertices big A, big B, big C, and sides A, B, little c. And we want to try to find a way to relate the sides. Now, things are going to be very, very different on a sphere. Does anybody know what's true about the sum of the angles of a triangle in the plane?
It's equal to 180 degrees.
It's equal to 180. What about the sum of the angles on a sphere, of a triangle on a sphere? Anybody know what's true on a sphere? So it turns out on a sphere, it's always greater than 180. And in fact, you can have the isosceles right, I'm sorry, not the isosceles, the equilateral right triangle on a sphere. Go from the North Pole down to the equator, move a quarter of the way around the globe, and then come back up to the North Pole. You will have 3 right angles. So you will have an equilateral right triangle. Now this triangle is huge. It's covering a huge fraction of the sphere's surface area. If you were to take a triangle that's really, really small on the surface of a sphere, what do you think would be true about the sum of its angles?
They're closer to 180.
Yeah, they're close to 180. So the smaller the triangle is, the flatter the sphere looks. You don't really see the curvature. And if it's sufficiently small, you're not going to have good enough measurements to detect the difference. And so when we are, trying to figure out what kind of geometry do we live in, and some of the handouts I'm going to give you for a fun meeting, talk about this, the accuracy that's needed, depending on how large of a sphere the universe might be, is just beyond our measuring capability. Now, if you're able to go huge distances, all the way down to the equator, then that's large enough that you can see, yeah, we're not on a plane. This is 180 degrees. Nope, this is 270. All right. So what I want to do now is talk a little bit about spherical coordinates. If you are a physics major or potential physics major taking a physics class, please say yo right now all at once. I know how many of you I have.
Hi.
Hello.
Me. Hey.
All right, so we've got a couple. So one of the things that's quite annoying is the physicists and the mathematicians have slightly different notation at times. We have different notations for spherical coordinates. I was a double major, I was physics and math, and I learned spherical coordinates in physics first. So I always have to fight when I'm teaching a math class to use the mathematicians' conventions. It doesn't really matter. You want to be careful. How many econ people do I have here?
Hi.
You go.
Okay, so we've got a few econ people. So have you seen supply and demand curves?
Yes.
Yeah.
Yes.
Okay, what's the units of the horizontal axis? Is it price or quantity?
Quantity.
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 Is it possible for you to put price on the horizontal axis? Could you do that? Of course. You would then be using the opposite convention of everyone else in the field, and they would hate you, but you can use whatever convention you want. You want to use the same conventions other people are so that they can read what you're doing. And so over here, the way spherical coordinates work is if you have a point on the sphere, rho is the distance from the center of the sphere to where you are on the sphere. Phi is the angle coming down from the z-axis. And then theta is the angle that you rotate around. So for instance, if I'm in the equator, my phi would be pi halves, or 90 degrees, because I'm coming all the way down to the equator. And then theta would go from 0 to 2 pi. With a little bit of work, you can show that this will give you every point on the sphere. I don't need my angle, phi, to go all the way up to 2 pi, because theta goes from 0 to 2 pi. So once I come down, I come to a circle that's parallel to the xy plane. It's just a little bit higher up. And so phi only needs to go from 0 to pi. Theta goes all the way from 0 to 2 pi. The physicists often use theta as the angle coming down from the z-axis. The reason mathematicians like to use theta for the other one is that this reduces to the polar coordinates, the r theta, which you've hopefully seen before. And so with a little bit of work, and we'll see this later in the semester, you can write x, y, and z in terms of rho, theta, and phi. And it makes sense that there should be a relationship like this. I have a point in 3 space. I need 3 coordinates to represent it, x, y, and z. I can also represent it as a distance from the origin. And then that's going to be then how far I come down from the z-axis, and then how far I spin around parallel to the xy plane. So since z equals rho cosine theta, z equals rho cosine phi, it's hard for me to do this even with the words in front of me. Since z equals rho cosine phi, that gives me a circle parallel to the xy plane of radius little r equals rho sine phi and angle theta. So you can see that now we have polar coordinates. We have my r and theta, and my r is a little bit reduced. It's not rho, it's rho sine phi. So what would the Pythagorean formula be on a sphere? So I'm going to assume that no one has studied the Pythagorean formula on a sphere. So this is all new. Well, what do we know? If A, B, and C are all small relative to the radius of the sphere, let's call that big R, then it should be approximately the plane of Pythagoras. We know that we could have an equilateral triangle with A equals B equals C, so we're a little bit worried about this. So the formula is going to have to be a bit strange. And then a little bit of thought tells us that, wait a minute, if we look at A over R, B over R, C over R, it could only depend on these ratios. Think of it as, if I change from measuring things in meters to feet, I'm not going to physically change the relationships. I'm going to just change the A's and the R's numbers by the same multiplicative factor. Their ratio is going to be unchanged. Another way of saying this is I'm just renormalizing things so that the radius big R is always 1. It's sometimes better to keep the R there. Maybe big R is going to infinity just because it might be easier to visualize. And I want to look at what happens in the limit as A, B, and C are very small relative to R. So A over R, B over R, C over R are all going to be small quantities. And then a little bit of thought gives maybe the insight, maybe it should somehow involve maybe the cosines, or maybe even the cosines and the sines of these quantities, because arc length is related to an angle. So this is why we use radians when we measure angles. The derivative of cosine is minus sine. The derivative of sine is cosine. This only works when we use radians. If you use degrees, you have this pesky conversion factor of 180 over pi. But if you take a circle of radius 1, then the arc length is equal to the measure in radians of the angle that it forms. And if you think about this, if you take a quarter of the circle is going to be pi halves in length because the whole circle has perimeter 2 pi, and the angle is 90 degrees or pi halves. The total angular measurement is 2 pi, which is the same as the perimeter of the circle. This is why we use radians. It makes differential trigonometry very easy. And so it might not be unreasonable to look at cosines of these angles, as arc length is related to angle. So you are not required to have done Taylor series before taking this class. We will do Taylor series later. So the whole point of Taylor series is to expand upon what we've done in Calculus 1. So in Calculus 1, we do the tangent line approximation, that a function is well approximated locally by the tangent line. Well, Taylor series just takes this a little bit further. Rather than just using a line, what if you used a parabola? What if you used a cubic? What if you used a quartic? Or more generally, what if you tried to use some kind of nice infinite sum? Then you need to make sure that the infinite sum converges. And a good part of the course towards the end will be dealing with how do we know this converges? And so we have the following infinite formula for cosine of u. And it turns out that this converges no matter what value of u you take, because the factorials are growing so rapidly. And if u is very small, then u to the 4th is much smaller than u squared. U to the 6th is much smaller than that. Think of u as 1 over a million. 1 over a million squared is negligible relative to 1 over a million. And so cosine of u is approximately 1 minus u squared over 2 when u is small. So if I take the cosine of a over r, b over r, and c over r, if I just look at the first non-trivial term, I get 1 minus 1/2 a squared over r squared, b squared over r squared, and c squared over r squared. And now here's the great idea. If I multiply the cosine of a over r and b over r and compare that to the cosine of c over r, I get 1 minus 1/2 c squared over r squared. And when I expand the two cosines on the right, I get 1 minus a squared plus b squared over 2r squared plus a squared times b squared over 4r to the 4th. Well, remember, we're saying a over r and b over r are small. So the first term is on the order of a over r squared, or b over r squared. The next one is of the form a over r squared times b over r squared. It's going to be much smaller. And so because it's supposed to reduce to planar Pythagoras when r goes to infinity, we see, yeah, c squared is looking like a squared plus b squared minus 2ab squared, 2a squared b squared over r squared. As r goes to infinity, it does look like c squared is a squared plus b squared. So this is not a proof, but this is strong evidence that maybe there is a formula like this for Pythagoras on a sphere, that the cosine of the hypotenuse is the cosine of the other two. Now, of course, things are going to be very interesting if we have an equilateral right triangle, because in an equilateral right triangle, all the angles are the same. Well, if all the angles are 90 degrees, what's the cosine of 90?
0.
0. So we would get 0 equals 0 times 0. Good. So the equilateral triangle, the equilateral right triangle is at least consistent. So one of the inputs we need, and this is going to be one of the first things we start when we do new material, is the dot product. So if I give you two vectors in Rn, Rn is just a n tuple of n real numbers, v1 through vn, w1 through wn. We define the dot product to be the sum of the component-wise products. So it's going to be v1, w1 plus all the way up to vn, wn. And one of the big theorems we prove is that if we have two vectors v and w, and we want to calculate the angle between them, then v dot w equals the length of v times the length of w times the cosine of the angle between them. And we calculate the lengths of the vectors by using the Pythagorean theorem. So this was one of the reasons why I wanted to prove the Pythagorean theorem today, because it's extremely important. So again, right now, this is meant to be a high-level overview of some of the topics we're going to see in multivariable calculus. We're going to see this thing called the dot product. We're going to have this theorem that the angle is related to the dot product and the lengths. This makes sense. You know, if I double the length of v, that shouldn't change the angle between them. And if I double the length of v, I double the dot product and I double the length of v on the right, so there's no change. So again, whenever you see formulas, you always want to ask, is this formula reasonable? It makes sense that I should have a product of the lengths of v and w on the right, because the angle is not going to change if I rescale the lengths of v and w. And I guess one of the things that's worth remarking is the angle between v and w is the same as the angle between w and v, and we do see this kind of symmetry. All right, so you can prove this by using the law of cosines. I'm going to just leave the algebra on the slides here. I'm not going to really go into it because we will do that later in the semester. We now take 3 points on the sphere, and we want to try to calculate and see if the proposed formula works. Without loss of generality, we might as well choose one of our points to be on the North Pole. And then I'll write down the coordinates of the other 2 points, calculate the vectors between them, and then we can calculate the angles between them. So again, I'm not going to go through all the algebra now. I'm just trying to show you what's going on. This is similar to what we did when we were talking about Newton's law of gravity. You might as well assume that you've got the sun and the point mass is just above the North Pole. Let's choose one of our 3 points to be on the North Pole. We can actually make things a little bit easier. We have to choose how far do we come down, and then once we do that, we have to choose how far do we spin over. So we might as well, we have some variable phi, but we might as well choose theta to be 0 for at least one of the points to just align up the coordinate axes nicely. And when you go through and do all the calculations and calculate what the angles are and the dust settles, it proves spherical Pythagoras. And once you have that, you could go further. What's the next natural candidate? If you've seen hyperbolic functions, you could guess maybe hyperbolic cosine of c is hyperbolic cosine of a plus hyperbolic cosine of b. And the hyperbolic cosines are related to the standard cosines in a very nice way. So cosine is 1/2 either the ix plus either the minus ix. And we'll talk about why this is true once we get to Taylor series. Hyperbolic cosine is you just replace x with ix. It's the cosine of an imaginary angle. And so it turns out that there are such things as hyperbolic spaces, and this is the generalization of Pythagoras on hyperbolic spaces. We have a lot of formulas for hyperbolic trig functions, which they essentially inherit from the standard trig functions, which inherit these from the standard exponential function. And so just to briefly conclude, there's always the opportunity to generalize. So take something that's been done and try to push it further. Try to ask, where else can you look at this? Different proofs highlight different aspects, and they can provide different benefits. So just because something's been proven doesn't mean that this is the only way you should prove it. And you want to try to get a sense of what to try, what might work. Don't be afraid to try something even if it doesn't work out. You try it at first, see if it works, and if it doesn't, try something else. The more things you try, the more chance you have of finding something that's going to work in the end. And look at special cases, look at extreme cases. I'm a huge fan of extreme cases, and it often gives you, okay, well, I know what's going to roughly be true in this setting, so whatever formula I get has to work in this case. All right, so this is a good place to end for today.